As we begin with Module 6, we are going to be talking here. We're going to cover three modules which are basically overlapping in the concept of we'll be working with bisectors, we'll be working with altitudes, we'll be working with medians. We're going to be working with things all dealing with some form of intersections inside my triangles. So beginning with a perpendicular bisector, well, just understand what is a perpendicular bisector. Is a line segment array that passes through a midpoint of a segment and is perpendicular to that segment. So CD would be my perpendicular bisector. It passes at a 90-degree angle perpendicular, and it bisects those two pieces in half. So those are understanding that point is on the perpendicular bisector of a segment. If a point, then it is equidistant from the endpoints of that segment. Now, we can now learn a lot of things at that point. So if, again, this is equidistant, so those two things are equal, I know then that this would be 90 degrees. They're telling me in this case, if CD is a perpendicular bisector to AB, then AC is equal to BC. Okay. If you have any doubts, we can see that that is the that would be the hypotenuse. We have a leg, but if we didn't go that fast, I know that CD is equal to itself, and then therefore I do have two triangles here that would be congruent. If those two triangles were congruent to each other, then I end up having corresponding parts of congruent triangles are congruent, and then therefore I would know that the hypotenuse would be the same. So by understanding that perpendicular bisector theorem, we now can determine a lot of things using corresponding parts based on some of the rules that we've already learned. And then the converse to that just says that if a point is equidistant from the endpoints of a segment, then it is on a perpendicular bisector. So going forward and back, if you have a perpendicular bisector, then these are equidistant, or if these are equidistant, then that means you have a perpendicular bisector. Using that perpendicular bisector, again, if FG is a perpendicular bisector, FG is the perpendicular bisector to EH. So again, we know then that this is equal to this. We know that we have congruent angles here, and I know that this is equal to itself. So those two triangles are congruent. Therefore, I know again that this piece, those two things are equal. So I can make those two things equal to solve for the value of A. And in doing so, we made them equal to each other. There's obviously some inverse operations here they didn't put in, to get us where we were at. But understanding that ultimately we found out that A was equal to 9, we substituted in and find out that this was actually 21 units, and that is 21 units. Okay, so again, how would we use that? So looking at this, we know that this is congruent to this is congruent to itself, so we know then therefore the hypotenuse is going to be congruent to the other hypotenuse, because we, if nothing else, we have side angle side congruency. Okay, so we know that corresponding parts are corresponding parts of congruent triangles are congruent. So we know that those two things are equal, so we can substitute over here that 2x plus 3 is equal to 4x minus 7, doing your inverse operations to combine like terms. Add 7 to both sides. And then 2x is equal to 10, or dividing by 2, x is actually equal to 5. So if I substitute that in for RT, that would be 4 times 5 minus 7 equals 13 units. Okay, so there you go. We solve for our variable, then substitute it back in to find the length using my perpendicular bisectors. The converse works in reverse. So it says if we know that these z and x are equidistant from point W, then we know that that is a perpendicular bisector, and then that is congruent to that. And then, of course, this one would be congruent to itself, but it wants us to find out what in the heck is equal to xy equal to. Well, if those two pieces are equal, then it should be equal to 22.4. So using those definitions. And then here in our check, wy, again, we know that that is equal to itself. We know my hypotenuse is equal, and then we know this should be equal. So therefore, wy should be 3. Okay, so just making sure we understand how to, label things and use it. Perpendicular bisectors. Okay, so when 3 or more lines intersect at a common point, the lines are called concurrent lines. The point of intersection of concurrent lines is called the point of concurrency. And then the point of concurrency of perpendicular bisectors is the circumcenter. Okay, so perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. So let's look at that. Here, just looking at this, if these are perpendicular bisectors, and if BF, find BF if D is the circumcenter. Okay, so this point right here would be the circumcenter, and they said by definition that is where my perpendicular bisectors intersect. So I know that DF is a perpendicular bisector, DE is a perpendicular bisector, and GD is a perpendicular bisector. So that tells me then that I know that this is congruent to that, that is congruent to that, that is congruent to that, this is congruent to itself, that is congruent to itself, and that is congruent to itself. And then they told me that this segment, that the lines all to the vertices were all the same length. Okay, so we know that those 3 lines are congruent to each other. So then it tells me that AC is equal to 9. So if the entire length is equal to 9, then this side is equal to 4.5, and this side is equal to 4.5. DE, they stated, is 1.83, and DF is 1.53. I got that backwards. 1.83, 1.53. Okay, and then it says because DE bisects AC, it's 1/2, so we came up with 4.5. We can use the Pythagorean theorem. They're trying to find BF. All right, so we want to know what this length is right here. We can use the Pythagorean theorem to find out what this length is, because this could be B squared, this could be A squared, and we can find C that way. But what did they do? Yeah, that's what they did. Okay, so then we know that DC squared is equal to A squared plus B squared, and then they found out that D squared is equal to 23.6, did the square root of 23.6, and DC is approximately equal to 4.86. So there you go, the positive square root. You use a positive number because it's a distance, it's a length, that has to be a positive number. So 4.86 approximately. So then once you find that, 4.86, then we know this one is 4.86, and this one is 4.86, because that's part of the definition of the circumcenter, is that they're equidistant from the vertices of the triangle. And then they were able to plug that back in and do the Pythagorean theorem again to find out, this would be C, B, A, to find out what that missing length is we're looking for. So that's what they did here, is they plugged it back into the Pythagorean theorem and found out that BF is approximately 4.61. Okay. And then there we go. Now, doing the same thing here. Let's see, have they got everything labeled? SV, okay, so here's my circumcenter. So let's see here, PS is 4.25, so that makes this 4.25, and that makes this 4.25. QR is going to be 7.79, okay, which means that this length right here should be 3.895, I'm thinking. Let's see. 7.79, I don't have a calculator on me, divided by 2 is 3, 1, 7, 8, 16, 1, 9, 9, 5, yeah, okay. And then this is 3.895 because they are the same. And then it says, if necessary, we're looking for SV, this length right here. So we can use the Pythagorean theorem. You have a squared plus b squared is equal to c squared, and this would be c a b. All right, so as we do the Pythagorean theorem to solve for that, you have a, b, c, so a squared plus b squared equals c squared, and then I subtracted b squared from both sides, whatever that mathematical value is. So b squared is going to be 4.25 squared minus 3.895 squared, which came to approximately 2.89. I rounded. Finding the square root of both sides, then b is approximately 1.7 units. So there you go. That's using the Pythagorean theorem to come up with the value within the triangle based on the perpendicular bisectors and using those characteristics. Here, using perpendicular bisectors in design, Alonzo wants to install a fountain in his triangular garden. Where should Alonzo place the fountain so that it is equidistant from the vertices of the garden? Okay, so equidistance from the vertices of the garden. We know that perpendicular bisector, so we would cut everything in half, right? So this length, this side right here, the perpendicular bisector would make this side equal to this side. So my perpendicular bisector would travel this direction somewhere, right? And then my perpendicular bisector over here, I would have to do the Pythagorean theorem. And here they want us to use a compass to construct. Be a little bit difficult here, but we could find the midpoint between here and here. Finding the midpoint there would be approximately right here. And I just, estimated based on slope. If I travel down 1, 2, travel down 12, and then over 8, the midpoint should be about down 6. We traveled down 10 over 8, so the midpoint should be traveling down about 5. 1, 2, 3, 4, 5, and then over 4. So that should be my midpoint, and then traveling at a perpendicular puts me right about there. And doing the same over here. Perpendicular. And then approximately right there is where my fountain should be. But again, it is an estimate. Because that shouldn't be, it should be more like that. More like that based on the slope. So there you go. And then doing this, the other example, and it says Lana wants to install skylights in her a skylight in her bedroom, and the section of roof where she plans to install the skylight has an incline and is triangular, the vertices. Okay, so they've given us the vertices. Where should the center of the triangle be? Well, we know that perpendicular between the perpendicular bisector between x and z should be there, going this direction. And then, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it should be approximately 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4.5. Right about there and there, going like that. So my perpendicular bisector is going to be circumcenter is going to be approximately right there. So we'll do more of this with actual paper, but just being able to understand what the perpendicular bisector is. For angle bisectors, angle bisector theorem states that if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So if this angle is equal to this angle, then D and E would be equidistant from point F. There you go. And then from the sides of that angle, if DF bisects DBE, FD is perpendicular to BD. So FD is perpendicular to BD. And then same thing goes for FE is perpendicular to BE. So again, we have that is perpendicular, that is congruent to itself. We have 90-degree angle, and then we also have this angle. So technically we have angle side congruency, which allows us to use those corresponding parts, right? Angle side, angle side. And then the converse to that, they're saying that if the point in the interior of an angle is equidistant from the sides, so if F is equidistant from the sides, then it's the bisector of an angle. So they're saying then we know that this is equidistant, so it would be the bisector, and then of course this is equal to itself, and we would have hypotenuse leg to be able to use that, because this would be my hypotenuse, this would be my leg, and of course this would be my leg and my hypotenuse for the other triangle. Okay, now using that angle bisector theorem, we know then that QT is going to be equal to TS, and we know I would say this is probably incorrect. That should be QT. QT is equal to ST, and we do some substitution, do our inverse operations, and we find out that X is equal to 3. And then substitute that in, and we find out that this is 20, so we also, if we were to substitute in, we would know that this is also 20. But we can make that leap if they're congruent. Checking it here, looking at this, we know that MS is congruent to SP based on the angle bisector theorem. So we can make those two things equal to each other and solve. So we have 3x plus 5 is equal to 6x minus 7. Using your inverse operations to combine like terms, we have subtracting 3x from both sides, and then simplifying, and then I'm going to add 7 to both sides, and then 3x is equal to 12, dividing both sides by 3, and then x is going to be equal to 4. So if we plug 4 in, 6 times 4 minus 7 should be equal to 17, I believe. 24 minus 7 is 17. So SP is 17 units long. Using the converse, again, if points are equidistant, then we are on an angle bisector. So if these points or those segments are equidistant, those are the same length, that means W is equidistant from both X and Z. That means we have an angle bisector, so this angle right here is also 38 degrees. So just understanding that relationship. So here, again, we have 2 points, a point that is equidistant from an angle. That means we have the perpendicular bisectors. That means this is an angle bisector. And then JKL should also be 37 degrees using the definitions. Okay. Now, angle bisectors of a triangle intersect at a point called the incenter, and that is equidistant from the sides of the triangle. So when we're using angle bisectors, and they are going to be equidistant from the sides of the triangle. So that's what we find out, is those distances are equal. 90 degrees, what do we know there? let's see, P is the incenter of that triangle, so we know that all of those segments are congruent. And then we can work with that. Looking at this image right here, P is the incenter. P is the incenter, okay? And then we know that this should be congruent to this, which should be congruent to that. We know that if we can use this triangle right here to calculate this value, because this could be A, B, C, and you could use Pythagorean theorem to solve that problem. Other things that we know that if this angle is 25.1, this angle is 25.1, this angle is 24.6. We know, of course, all of these things are right angles right here. And then using the angle sum theorem, we can probably find out if we know what this whole angle is worth, we can calculate this whole angle and then divide it by 2 to find out the little angles. And that's what they did. They said, okay, we have 49.2, we have 50.2, plus this corner over here is equal to 180 degrees. They went ahead and subtracted 99.4 from both sides, and they figured out that this LZJ was 80.6 degrees. And then if it is, let's see, what else do we know? If this is 80.6 degrees, and we know that this is 40.3, because the entire thing was 80.6. And there you go, using the information we have available to us. Here, find JF. Okay, I'm looking for this value, and I know I can find that value using this triangle, because I have two sides of my right triangle. This would be my hypotenuse C. I could call this A and this B. So in order to find B, I would have to take, again, A squared plus B squared is equal to C squared. A squared would be 9.4 squared plus that thing we're trying to find, B, equals 10.6 squared. I'm going to go ahead and do my inverse operation, subtracting 9.4 squared from both sides. I'm using the calculator for this. There's no reason for me to use the calculator beforehand and start moving bigger numbers. B squared is equal to, using the Pythagorean theorem, we find out that B is equal to approximately 4. So 4 once we round it. And then, so we know this is 4, and so JF is approximately 4. And then JAC, let's see here, JAC, we're looking for this angle in degrees. And what do I know? I know this is 33.9, I know this is 28.5, so 2 times 33.9 plus 2 times 28.5 plus 2 times angle JAC is equal to 180 degrees. And then we can work with that. So I'm going to go ahead and subtract. And there you go. I subtracted combined like terms and subtracted that from both sides. I find out that 2 times angle JAC is 55.2. So if I go ahead and divide by 2, that should give me my answer. So 55.2 divided by 2 is going to give me 27.6 degrees. There you go. 27.6 degrees. So again, using those properties and definitions. And let's see here, moving on to medians and altitudes. Median is a line segment within points that are a vertex in the triangle and a midpoint on the side of the opposite vertex. And they okay, so it's the midpoint. So our segment starts at the vertex and it travels to the midpoint of the opposite side. So we know that those two pieces are congruent. So it bisects those. It's not a perpendicular bisector, it bisects those. We know then if all of these, what happens is, since it's at the midpoint, then M, N, and L are all midpoints, and this is my N center. So we know that BM is congruent to MC because the midpoint is where it connects halfway through. Some of the properties that we know that medians, so these medians of a triangle intersect a point called the centroid that is 2/3. Hopefully I didn't just say in center a minute ago. 2/3 the distance from each vertex. Okay, so the entire length here, this is 2/3 of AM, sorry, 2/3 of the entire length, and this would be 1/3 of the entire length of AM, because this occurs at the 2/3 point, so the centroid. So if I'm trying to find something out, they tell me that BL, the entire length here, is 6. This is 2/3 of 6. This is 1/3 of 6. And think about it. 2/3 of 6 is 4. 1/3 of 6 is 2. So we know that this length is 4. This length is 2. So that's how we're using this information. So the centroid. Using this right here, looking at this, how can you find the coordinates of the centroid? You would have to find the midpoint. The midpoint between these two, you would have to find the midpoint. So you would have to find the midpoint here. And then you would connect those to the vertices of the opposite vertices, and we would find out that my centroid is located approximately right there. Mathematically, there's other ways to do this. I'm just sort of, letting you see what we're doing. Here, again, 2/3. The things that I know, BE is 9. The entire length is 9. And I know that BQ is 2/3 of BE. I know that QE is equal to 1/3 of the entire length. So again, this would be 2/3 of 9. This is going to be 6 and 3. Okay, and then we were able to, 6 and 3, because this would be 1/3 of 9, which is 3. All right, so with that, again, using some of this information, they've told me that PY is 7. This is 7. Well, I know that PY is 1/3 of LY, right? Because it's the little piece. So I can figure out what the rest of that information is, because I know that PY is 7. 7 is equal to 1/3 of LY. I'm going to go ahead and multiply by 3 to get rid of my fraction, because 1/3 times 3 is just 1. And then 21 is equal to LY. So the entire length is 21, and we know that this is 14, because it is 2/3 also. So there you go. Sometimes the math is a little bit more difficult, and a lot of you are probably saying, I did that in my head. That's great. Understand the process, and that way when it's more challenging numbers, you're not stumped just because you are worried about a big number. Let's see here. So in this check, they told me that SP is 3.5. And I mean, honestly, I know that SP is 1/2 of PZ, right? PZ. Or I know that PZ is 2 times SP. Mathematically moving that literal equation around. So I know that if SP is 3.5, then I know PZ is 7. There you go. Think about it. The entire length is 10.5. So, again, PZ is equal to 2/3 of 10.5, which is 7, right? And that's really the big stuff that we're supposed to be focused on right now. So we're going to go ahead and talk about altitudes. Altitudes are going to be the height of the triangle. They intersect at the orthocenter. 3 altitudes intersecting at the orthocenter. And altitude is a segment from the vertex of one triangle, one angle, line containing to the opposite side. And that tells me how high, what is the height of my triangle. The altitude does not have to be inside the triangle. Understanding what the height is the, the perpendicular distance from the vertex to the opposite side. And then here, so finding the orthocenter on the coordinate plane, we're having to use the distance formula, having to use slope, having to do a bunch of different things here. Let's see here, graph ABC. So AB. Okay, so once I've gone ahead and graphed my triangle, in order to, see here, find the coordinates of the orthocenter of ABC. So what do we have to do? Remember the altitude is perpendicular, and then what we have to do is, in order to find these perpendiculars, we would calculate the slope of AC and then find the perpendicular slope to it, which I think we calculate. If you look here, the slope is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So the slope here is equal to negative 3/2. So a perpendicular slope would be equal to 2/3. So I'm calculating this altitude right there. So I would go up 2/3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. So this line is my altitude. And then I could do the same thing for the next one. A is going to be up 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So this slope of this line is 4/6. Negative 4/6, or negative 2/3. Then the perpendicular slope would be 3/2. So again, from here, 1, 2, 3, 1, 2. There's my perpendicular slope. So once we have 2, this one should be doing that, right? That should be my location. That should be my location of the orthocenter. So you have to do some slope computations and understanding what slope and the perpendicular values of slope, and then plugging them into equations of lines, okay, in order to graph them. So, but I was trying to show you here that once we know what the perpendicular slope is, we can just take it from the vertices and count those slopes to get what we need. So we'll get some practice on this in class. So again, we were talking about the altitudes, the medians, the bisectors, and all of these characteristics.